So hello, everybody. Some of you were here, many of you were here yesterday for at least part of the time. This is what we worked on yesterday, and we didn't quite finish what we needed to do with this yesterday. So we're going to be starting from where we left off. So if you don't have your stuff from yesterday, then, and we also had, of course, our nice implementation of the all function, which I'll show you in just a second. So if you don't have those things, you might want to type them really quickly. Yes? Huh? Right now?
Maybe someone else would have them do that?
No, you have to type. All right. I don't actually know. It is all about typing. I don't know. Let me see. This is what we want. Right? What do you mean? You just want me to like paste it into Slack?
Exactly with the backticks.
With the backticks?
You take from line 5 all the way up to 25.
Okay. Whoa, buddy. Okay. Yeah, you want everything all at once. All right, and then just paste it in the Slack? For real. I think I closed Slack though, because it's ZuriHac.slack, right? Yeah. Okay, I'm really glad that we're streaming this. This is great. So you just want me to put it here? Yes? Okay. Ready? There it is. You don't need the Haskell part at the top. That's from that's the markdown. Okay. All right. So that's where we were yesterday. Right? Does anybody who wasn't here yesterday want to ask any questions about this before we move on? Yesterday we talked a lot about recursion because strings, which is the data type that we're mostly working with here, strings are a kind of list. They're a type synonym for a list of characters. So that is less general than a list of A, right? It's actually quite a specific type. And so we talked a lot about how we recurse over lists. So does anybody have any questions about anything that we did here? You can see that in this version, if you weren't here yesterday, you can see that, for example, I went ahead and called that by its proper name, right? We had written a version of it ourselves that we called Pam. The version of it that exists in base is called map. And we left off talking about folds, and I don't have the papers anymore, but we had written a Boolean function called all using fold right and talked about that right there. So we had written this function here. We called it lob because we're very creative namers. We're just spelling everything backwards. So this was our version of a function that does exist in the prelude. So we can see it here. Now, there's a difference between the version that we wrote and the version that exists here, which is, what's the difference between this type signature here and the one that we wrote? The one that GHCI gives us and the one that we wrote. Right. We specialized ours to a list. Of course, we knew we were working with lists because strings are kind of lists. So since we knew we were working with lists, we specialized ours to list, whereas this one is not specialized to list. So the type of all that's in base is more general than the one that we wrote. It can be used with more list-like things than ours can. Any type that has a foldable instance. We're actually not really going to talk about the format type class very much, so it's unfortunate that it keeps popping up in type signatures. But there it is. So ours is a less general version of that, right? But still, the one that we wrote would work with more things than just strings, right? Because we did leave, rather than pointing, I guess I should do this for the people at home. So rather than specializing this to character to bool and a list of character, which is what we were actually working with, right? We left them as A's. So it's not as specific as it could have been or as monomorphic as it could have been, but it is less polymorphic than the one that's in base. All right, any questions on that so far? All right, so then the next step after we wrote our version of all that we didn't quite get to was to use it in this function isWord. isWord should take a string input and return a bool, checking that each character in the string is an alphabetic character. Does anybody remember how we check a character to see if it's alphabetic? Is alpha, right? From the... Yes. Can I not get back to Chrome? Okay. Okay, so we had it right here, right? And we talked about these yesterday. So if we use our all function and this is alpha function, we can write a function that we will call, where am I? isWord. We'll take that string in and return us one bool value for all of the list. Not a list of bools for each character, but reduce it to one Boolean. Only if all of them are true will we return a true. All right. And when you're done, of course, you'll want to load your file back into your REPL, right? Make sure everything type checks. Is alpha should be the first input, the A to bool function, that's your first input to all, with the string being the second input. All right, everybody ready? I think I already wrote it. If not, I can write it. All right. Oh yeah, well that was using ours. You can use the one that we wrote or the one that's in base. They both work the same, or they should work the same if we've done everything right. Okay, so this isWord function will take a string input that we've called XS, right? X's. And using this all function, using this fold, it will return true only when every character in the string is alphabetic. Any questions? No? No questions. Okay. Cool. When we left yesterday, did we have, we did. We had this already written, right? This, our combination. Okay, so we can move on from there. All right, so we're now going, oops, I wasn't supposed to show you that. All right, we're now going to combine them because one thing that you will notice about our isWord function is that it's going to return false if there is any white space. But we specifically wanted to be able to have palindromes that have white space in them, right? That's why we wrote the ignore spaces thing. So we need to get these things happening in the right order, right? We don't want to do isWord until after we've already gotten rid of the spaces. The upper and lowercase, that doesn't matter so much, but isWord definitely has to happen after the ignoring spaces, right? Because alphabetic, because white space is not an alphabetic character. Okay, so we're going to combine them though into a function that will check the whole input. I guess I just went ahead and wrote this. Yes, I guess I did. Okay, so I didn't hide this from you appropriately. So we'll just talk through it. Okay, so this function here is going to combine them in a way that will do things in the order that we want them, right? We have here a combination of several things that we talked about yesterday. So here's our string input, and we see it here, and then we see it here again. So we have our function composition here. X's will first go to ignore caps and spaces. The result of that then will be passed as the input to isWord. If isWord returns false, then we will return false. If isWord returns true, then we will apply isPalindrome to the string. So we didn't talk a lot about case expressions yesterday, but do you all remember them? Okay. So they're a little bit like conditionals, particularly when you're pattern matching on Booleans. They're very much like conditionals, where we just branch on the output of one function that returns a bool, right? If it's true, we go one way. If it's false, we go the other way. So if in this case, if isWord is true, then we want to apply isPalindrome to the string, right? I see some of you frowning at me, and maybe you've already seen what the problem is with this. Well, let's try it out. Do I have it written somewhere? I'm gonna have to just. Okay, nope, I guess not. All right, let me just get it then so we can look at it. If anybody wants to hazard a guess at what might be the problem with this as we have it written, go ahead. All right, I don't have to type, see, because I already typed it all. All right, so let's load this into a REPL. Everything compiles, so that means everything works the way we want it to work, right? No. All right, we're gonna go ahead and change our main so that it uses that function that we just wrote. Now let's make sure that still compiles. It does. All right, so let's try main again. It should wait for us to put input, and then it should apply our check input function, which will do all of the things, right? It will remove the spaces, it will remove the capital letters, it will test to make sure it's all alphabetic, then it will test to see if it's a palindrome. Yes? Right. Okay, so let's try it out. So we know this should be good, right? Good. But we also wanted this to be good. Is that going to be good this time? No. right? That's going to be a false. But we saw that we wrote this function that should be ignoring the spaces, right? That should be removing actually the spaces for us. So what's happening here is that this XS, that's the input, and this one are all the same, right? And so we haven't actually, even though we have applied this function to our string, when we return it down here, it's not the string that was transformed by this. It's the string that still has spaces in it. Okay? So that's one of the problems with what we've done here. It does compile, but it does not do what we want it to do yet. Okay. So another thing that we want to work on correcting today is that right now we're just returning a bunch of Booleans, right? We don't have a way to distinguish between this being false and, oops, right, main, and this being false. And that being false, right? So we just talked about why this one came up false, because we're not actually using the string that was where the spaces were removed, right? This one should be false because it's not even a palindrome. We didn't need to transform it at all, but it's just not a palindrome. And this one should be false because it's numbers, and also it's not a palindrome, right? All right, so we don't have any way with these Booleans to distinguish between different kinds of false. Does that make sense? So we're going to begin fixing that by using maybe. These are supposed to be slides, and I'm sorry, I'm missing apparently a different LaTeX package still. All right, so we talked a little bit about maybe yesterday. You might remember. Maybe is a sum type that is really similar to bool in a lot of ways, right? With word bool, we have two cases, right? We have false. Right, we can compare them directly here. With bool, we have two cases. We have false or we have true. But the false is just false no matter why something is false. And the true can't carry any information with it, right? It can't tell us why something was true. So we get very little information from Booleans. But maybe gives us the opportunity to carry around at least some extra information. Because when we apply maybe to a type and construct, for example, a maybe string type, then this just can carry around a string that gives us some kind of information. We also have another type called either. And either gives us more opportunities still. It's still a sum type, very much like maybe or bool, except for now we have two type parameters, which means we can apply it to two type arguments, and they can be different. And we can carry around information on both sides. Most commonly, probably, either is used where the left side represents some kind of error case, just like false or nothing, and the true represents some kind of, or the right, sorry, represents some kind of success case. That's a very common usage for either. It's not the only one, but that's a very common usage for either. Which means that we're using it a lot like bool and maybe, except for we get a lot more information with it. But let's start with maybe. All right, so we're going to try to rewrite these functions here. Is palindrome, is word, and our check inputs to use maybe instead of just returning Booleans. All right. Let's go through the is palindrome one together first. I'm sure that you're all capable of doing it by yourselves, but let's go through it together first, and then you can do the other two. All right. So the first thing that we're going to do is have a nothing, right? One of the problems that we just noticed in our REPL, I think, is that an empty string is going to be a palindrome. Now, that's really correct, right? Because a space is the same forward and backward, right? But that's not intuitively, that's not really what we want to call a palindrome, right? So we're going to modify our is palindrome function first by pattern matching on the empty string case and returning nothing for that. All right, we don't have a valid input, at least not what we want to consider a valid input. Okay, and then we're going to move we're returning here a maybe string, and that's so that we can return a message, right? So we're going to move our essential palindrome checking logic here. We're going to move that into a case expression so that we can return different messages based on the outcome. So if that is false, then we did have a valid input, but it's not a palindrome. So that's the message that we want to return. And if it's true, then we'll return the message that it is a palindrome. Now, because we're using maybe, both of those have to be sort of wrapped in these just constructors, right? Because that's how we construct a value of the type maybe, by applying just to some value of some other type. Since that's a string here, right? Remember the A's have to match. The maybe A and the just A have to match. So since we have a string at the type level, at the term level, we need some string literal. Does that make sense to everyone? Any questions? All right, so we're going to do next is word and check inputs. Let's convert those to using maybe as well. Yes.
So for the word, so if it contains any numbers, it's not the word anymore.
That's my rule. Yes. You can have a different rule if you want to, and that's okay. But because there's also you could use is alpha num. That's also in the same package. And so you could use that instead of is alpha if you wanted to allow numbers. All right, how's it coming? Does everybody have is word done? Or something working? Okay. How about check inputs that we're working on now? Oh, well. It should. Are you arguing with having an S on it?
I don't care. No, that's the function does the same job.
Oh yes.
Then I don't care.
Okay. Yes. Did I make a mistake? Oh, I did. Yes, it's the same function. There you go.
Phew.
I know. Sorry about that. So yeah, same function, but let's return maybes.
You should only cover the jump case, not the nothing case.
I have a nothing case. All right. Do you have an is word that looks something like this? Yes.
25 line can be combined with the case state kind of pattern matching.
Yeah, the 25 line doesn't really need to be there at all.
Yeah.
Yeah.
If I say pattern matching, case is equal to blank, return nothing like.
You want to put the empty string case inside this case, inside here.
Kind of that, yeah. After that case empty, return.
Oh.
Nothing.
I don't know. Does that work?
It's correct.
Is that what you did?
No.
Oh, okay. I don't think. I mean, I don't know, because I always do it like this. I always handle the. And so I actually don't know. Does someone here know? Can you put the empty string inside of here? I don't think so, because all is alpha. Because what you're pattern matching here is the results of all, right? All can only return true or false. And so you have to be pattern matching only on the things that it can return, that all can return. And so I'm pretty sure that this has to go up here. I'm not positive. And it doesn't really have to be there because we have other functions like the is palindrome that'll catch empty strings, but for completeness sake. And it also doesn't really have to be there because all is alpha is going to return false if it's an empty string anyway, right? I think.
For the character of empty string
For
the characters are alphabetical. It's an empty. There is none.
If it's all alphabetic?
It's an empty string, then all of the characters of an empty string are alphabetical. Yes.
I thought white space said false if it's. Let's find out. You're right. I didn't think, because it's not really white space. That's why, right? If it's space, then we get false. But if it's empty, then it will return true. Good call. I didn't realize that. So if it's actually an empty string, then it will return true, because that's the identity. When we wrote it with the fold, we talked about that, and yet I've forgotten. Thank you. Does that make sense to everybody, what we just said? Why that's true? Because if you have an empty string with one white space character in it, right? That'll return false, because it's only white space inside. But if you have actually an empty string, then remember when we wrote it with the fold yesterday? How true is our identity value, and we talked about with fold that if it is given an empty list, it returns that start or identity value, and so it'll return true if you right here. And he was pointing that out to me. Okay. All right, so we're all good with isWord? Okay. Yeah, it won't really change anything if you've decided to use isAlphaNum instead, and so you have numbers allowed. All right, so then let's look at this. Okay, so we have still a string to maybe string. We've once again pattern matched on the empty strings, and we'll return nothing, indicating that we don't have a valid input. We've done that now 3 times, so surely we will catch the empty strings now, right? All right. Then we have a case expression that has our composed function inside, right? So first, this x's will get passed to ignore caps and spaces. The result of that, right, will get passed to isWord. isWord now will return either a nothing, if it's an empty string, which it shouldn't be because we pattern matched on that here, or if that's false, right? So when isWord returns nothing, then check input will also return nothing. If this expression here does succeed and we've returned just x's, right, then we are going to rename that string so that we will be sure and get the transformed string. Okay, because ignore caps and spaces removes capital letters, right, or changes them to lowercase, and it removes spaces. So it's actually creating a new string after it operates on one string, because it doesn't mutate the string. It creates a new string for us that just doesn't have any spaces in it or any capital letters left, right, where all the capital letters have been transformed. So isWord doesn't transform anything, but this function does. So this new string that we've created, we get this new string from ignore caps and spaces. We pass that to isWord, which checks to make sure that it's all alphabetic characters. And then that new string, we have to give it a new name right here. By giving it a new name, then, we've signaled that we want the new string, not this one, but the new one, after the spaces and the capital letters have been removed. And so then we can apply isPalindrome to this new string. And now it should work the way we actually want it to work. But we will not, oh, don't look at that yet. There we go. Let's get that out of there. All right. But we don't want to take that for granted, so let's check it out. Okay. Everything's working, right? Everything's compiling. So we'll try main again. And this time we get success, even though we had space in it. So now we can tell that we are returning the string. We're passing the string that has the remove spaces to our isPalindrome function, right? So we can tell that. And in the bargain, we're actually telling somebody more information, our user, right? Our hypothetical users. We're telling them more information than just true or false. We're telling them what actually, right? What was true and what was false. So same thing here. We can try it with a bunch of gobbledygook and we got nothing, right? And nothing is maybe a little bit less informative than we could be. Right? We could use either to pass an actual error message saying like this is not a valid input. We do have this where we can return now this is not a palindrome. So this is definitely improvement over Booleans, right? We're able to convey a lot more information with this than we were with Booleans. All right, any questions about what we've done so far?
Yes, you.
Yes.
Lines 35, 36.
Yes.
35, you specify nothing as a result.
Yes.
And on 36, you don't use a just statement. Or use palindrome. It's S prime, right?
Yes.
Why so? Type definition says for check input.
But is palindrome is returning the justs for us.
Just.
Yes. Mm-hmm. So that's a really good question. So you can tell, for example, if you get the type of is palindrome, we know what the type of that function is, but you can see, for example, the type of is palindrome applied to some string. It will tell you that its type is a maybe string. And so down here, when we applied is palindrome to a string, this is already a maybe string value. Does that make sense? And so we don't have to put the just, right? We didn't have to do this. Seriously, okay. We didn't have to do that because is palindrome applied to a string is already a maybe string value. Any more questions? Okay. So let's go back and see what we're doing next. Ah, yes. I said, well, we're done now, right? Because we've been using functors and monads now. So now you know what functors and monads are because you've been using them. What are the monads here? Does anybody know? Yes. There's two. Well, we haven't used either yet, but either is definitely monad. IO. String is also, yes. Oh, 3. And maybe. Yeah, so those are the 3 monads that we've been using so far. We haven't really done anything cool with, right? So the monads that we have here so far are list, because we're using, right, strings. IO, we've been sort of covering that one up in our do block in main. And maybe. All right, so we just saw that we had the type IO for main, but we haven't really done anything interesting with it yet, right? But look at, we've written a whole program without even having to think about what monads are. Aren't we proud of ourselves? All right. So we're going to start breaking this down now to figure out what we mean then when we talk about monads. Now, there is a type class called monad. The main type classes we've talked about so far really are foldable, because that keeps popping up in type signatures, right? Really obnoxious. And we talked a little bit about the equality type class when we talked about our very first function, right? So quickly, can anyone tell me what a type class is? You don't have to do it quickly. But can anyone tell me what a type class is, either from what you knew before or from what we've talked about so far? Yeah.
It's a bunch of function signatures.
It's a bunch of function signatures. That's right. A type class is a collection of operations, right? A collection of methods. We have to be careful with a lot of these words, operations and methods, because they mean slightly different things in different languages, but it's a collection of functions. In the type class declaration, we just have their type signatures, and they're as general as possible. In the instances that either exist for us in base, or that we write, or that we derive, that's where the implementation of those type signatures for our specific types exist. So there's a type class called monad. We're going to get to talking about it, but first we're going to start by talking about functors in general, in the functor type class. Why are we going to start with functor? Because monads are a kind of functor. So there's also a type class called functor, and it is what we call a superclass of the type class monad, which means that anything that is a monad also has an implementation of the functor type class. Okay, so those are a lot of, that's a lot of words. Let's see what we can figure out. All right, so let's start by following the types. All right, we talked yesterday about how getLine has the type IO string. Okay, so we said we were just gonna kind of ignore that for now, right? That this is you can call it a function, and that's okay. It's in some senses not a function, and it's more, some people describe it as a recipe for getting a string, right? You're going to get a string from somewhere else that's not in your program, right? So this is a string that has to come in from somewhere, which means that, like all IO actions, it has a lot of possibilities for stuff to go wrong. I mean, typically getLine doesn't really go wrong because we're just typing into a terminal, but like all IO actions, there's a lot of possibilities here, right? So we treat them a little bit differently in Haskell than we treat other types. And the IO type is also a little bit strange in that we don't what we call expose the data constructors of IO. So when we query things in our terminal, right, we can see here that it is a new type wrapper around, oh, wow, all of that mess, right? And we can't really do anything with this. This is not something that we could write for ourselves the way we can write maybe or either or bool, right? All of those we can just sort of write for ourselves, and their data constructors are exposed when we query them. And when we query either, there they are. There's the nice, simple data constructors. And we could write those for ourselves. We could rename it and write our own either type, and people do all the time because it's a very common pattern. But IO is a little bit special. But the thing about IO is that you don't really have to understand all of that stuff that's going on underneath. What we care about here is that it has a functor. It's a monad as well. It's also an applicative. It's also a monoid. So that's how we use, right, IO. So when you're in something like a do block, like we've been here, right, this is all you can see from the type, this is all in IO. This is all in the IO monad. But it doesn't really matter, right? Okay. However, let's get now to understanding what these are all about. So we have getLine, which has the type IO string. And we know, because we're passing that as an argument, right? We're calling the output of getLine. We're calling this IO string. We're calling it word. And we're passing it somehow to check input. And what kind of argument does check input take? A string. Not an IO string, just a string. So between this line, right, where we get an IO string, and this line here, what's happened to the IO? It hasn't disappeared.
It's changing.
Sort of, yes.
The IO was flat mapped so that we could have this.
Yes, yes, exactly. All right, so you remember when we wrote map, when we wrote our map function, right, we called it PAM, but when we wrote our map function, we wrote a function that had this type signature, right? Takes a function from A to B and a list of A, and for every A that's inside that list, we apply that A to B function, and we return a B at the end, or a list of B, sorry. We return a list of B at the end. All right, well, list is just a type constructor, just like maybe. And also just like IO. Well, it's different from IO in some very important ways, but also sort of just like IO. So what we need is a map function that could, instead of applying this A to B function to every element inside a list, we want a function that will take an A to B function and apply it to an A that's inside a maybe. Do you think that's a function we could write? We'll call it maybe map. And we want to take an A to B function. And instead of a list of A, we want to take a maybe A. And we want to return a maybe B. Now this is going to be easier than writing map was because we don't have to worry about recursion this time, right? There's only one A inside of a maybe A, not potentially infinitely many of them. So how are we going to start with that? We're going to have a function. Well, yes. So if the function would be applied to a nothing, then what should we return? A nothing. And if we instead have a function and a just x, right, just function x. Okay, make sure that I've done everything right. Can't remember what ran, so. Okay, well, it's certainly type checked. So let's make sure that we can actually use it. All right, so let's try. We'll do some addition this time. We have a partially applied addition because we just have an A to B function, and we will apply it to some number inside of a just. Looks like it worked. Okay, so now we might be getting a sense that this map function might have a more general version, right? If we've written it, if we can have it for lists and we can have it for maybes, then the odds seem good that we can have it for some other types as well. It turns out that there's a whole lot of types that we can have it for. We can have it, for example, we can have it with, I'm going to need to import. Okay. Well, now we know that this, oops. We know that this get line, right, is an IO string. But we want to take the string and fmap or map to lower over all of it, right? What? It's on then. Huh? It did. In the second argument of namely getLine, but yes, but we're mapping it. No, I think we have to. Huh? No, first is the function. What am I doing wrong?
Das nicht die precedent.
Yeah, but it thinks that the string is an array, right?
At least.
Yeah.
Yeah, it thinks that it's expecting. Why is it expecting IO character? I mean, it's expecting IO character because. Right? Yes. Because we can definitely do this, right?
But F mapping on the IO one, I do not on the system.
I have to fmap twice. Yeah, he's right. I have to fmap twice. Fmap. Oh, yeah, okay. Never mind then. You can fmap over getLine. I'm just not doing it right, and I'm sorry. I'm very tired, and so that's my excuse. Okay. But there is a functor instance for IO, so we can in fact fmap over it, and we'll just give it up because I need to fmap twice. Okay. Anyhow, so the type of this fmap function that we've been talking about is this. All right. We have a functor constraint there that tells us that the f's in this type signature have to be some type that what? Yes? Yes, right. So the f's here, the f's right here and right here, both have to be types that have an instance of functor, which includes list and maybe, which we've already seen. It does include IO, and I just messed it up, and a bunch of other types. Either as well, although either is a little bit weird, and we're going to look at that in just a few minutes. Tuples? Yes.
There is a functor IO.
Yes.
So getLine is not inside the functor IO. That's why we don't.
Well, it's because it's a string, and so if you were doing something on a string, so for example, if you were yeah, you can fmap a string function into an IO string, but if you're going to, but since IO and the list are both functors, and so you have to have two fmaps, then you're double fmapping to get all the way inside to the stuff. I mean, yeah, it's because my choice of function to fmap, right, is a character function, not a string function, so it was poorly chosen. Huh? Yes, I think so. Yeah, or I think, you know, yeah. Yes, you could use one of the string functions, and then I think it will work right. Like you could do this, maybe. Yes. Let's see if you use it. If you use fmap, this is an IO string, but since this takes a string and not a character, then we only have to fmap once to get it to apply to the string. So this function was poorly chosen on my part. Right. Why is there no IO in the output? Well, we've already seen what it is, right?
This is because it outputted.
Yeah. So there is, it's just not showing up because we're in GHCI. And GHCI sort of always, you know, IO is always happening in GHCI, right? That's the only way it could work. So, okay. So next, let us, then we have talked about the either type. We could refactor all of this to use either, but I think instead we will just, do you want to do that? Or should we just move on to talk to type classes? Ready to move on to type classes? Awesome. Okay. So let's talk about the functor instance for either then, because it's an important one to talk about. So we've seen that I'm gonna need a new. All right. So we've seen that it just happened. That either has two type parameters, right? We have a left A or a right B. And we know from our previous maps that we've worked with, because we're going to talk about the functor type class for a little bit first. So from the previous ones that we have worked with, we have like list of A, right, is either an empty list or list or A cons onto a list of A, right? And maybe has one type argument as well, right? So each of these ones that we've worked with before only have one parameter, right? Just an A. So they're functor instances then, which, because fmap is the primary function, primary method of the functor type class, right? And so we look at it, we can see that it really only has the ability to act on one thing, right? It can take an A and transform it into a B, right? It can take this A and transform it into this B. So it can take a maybe A and transform it into a maybe B, or it can take a list of A and transform it into a list of B. What it can't do is take an either AB and transform it into an either CD. We do have a type class for that called bifunctor, but that's not what functor does. So functor can only do something with one of the values. And so when we write a functor, when we write an fmap for either, right? Go ahead and call it what it is. An instance of functor for either A. We have to partially apply the either. We've been talking a little bit about partially applying functions without really talking about it, right? So when we've had things like, you know, we've done map +2 over some list, right? That +2 is a partially applied function, right? Addition needs 2 arguments. We've given it one of it and then passed it to a list so that it'll apply that partially applied function to each element in the list. When we're talking about it with an infix operator, a little bit of trivia for you. When we're talking about it with an infix operator, this is technically called sectioning. So, but it's just a partially applied function, and we can do it with functions that are not infix operators as well. So we've talked a little bit about partially applying functions, but without really talking about it. Do you all understand how partially applied functions work? What's going on with partially applied functions? How can we do that? We're returning new functions. That's right. We've been talking loosely, casually, as Haskellers do, about functions that take 2 or 3 arguments. And sometimes people will make a point of reminding you that every function in Haskell takes 1 argument and returns 1 result. And that is actually always true. Every function in Haskell takes 1 argument and returns 1 result. That result might be another function. But that's how we're able to partially apply things and pass them around as new functions. Because we have what's called currying, and we have it currying by default, which means that type signatures such as this one, right? I mean, I just said that it takes 1 argument and returns 1 result, and this would seem to be a lie, right? How is this thing only taking 1 argument? Well, this function only takes 1 argument and returns 1 result. This is 1 argument, and it returns this, which is 1 result.
So it seems those arrows are right associative.
The arrows are right associative. And that's why, for example, like this set of parentheses has to be here. Because we are taking the first argument, or the only argument, if we want to be pedantic, right, is a function. And so that set of parentheses has to be there, indicating that that argument has to be a function. Because otherwise, with the right associativity, if you didn't parenthesize that, what you would really have is this. And really, in some sense, you do, because A is 1 argument and it returns, the B, right? But that's not what we want, right? We're not actually giving an A to our F map. We have to give an A to B function. Does that make sense? So the arrows are right associative, and that's why when there is a function as an argument, then it has to be parenthesized. These parentheses are conceptually here, but are syntactically superfluous. They don't have to be there syntactically because Haskell is sort of doing this by default. So you can create a function. For example, you could create a function called lowercase that was equal to fmap to lower, for example, and not apply it to a string, and then later apply lowercase to some list or string. Right. And so this can be a function. Right. Lowercase can have a name, be a named function, even though fmap has not been applied to all of its arguments. And we can pass, this around and use it as a function, which is really convenient if, for example, you want to be I mean, to lower is not really very type agnostic, right? We know it's going to have to take a string, or it's going to have to take a list of characters, right? Because to lower works on characters. But if we had something instead of to lower that was more polymorphic, and so we wanted to be able to use lowercase, for example, on maybe different kinds of inputs, right? Being able to pass this partially applied thing around to possibly different types of lists can be really convenient. But this is sort of on by default. All functions have this right associativity. And so they are always taking, one argument, returning one result, which means we can always partially apply them to one argument and have a new function. And if we really want to get fancy, if we had, say, a 3-argument function, we could apply it to one function and return a new function and name that. And then apply it to 2 and name that and return that, right? And then it's still only lacking 1 argument. In fact, I think there's a chapter in the Haskell book that I wrote that does that quite a lot. So if you want to see that in action, we do it repetitively. But it's sort of an important feature of Haskell to be able to do that. And it's going to be important now here. I think it's where, right? Yeah. I haven't written an instance in a long time. All right. Yes. There they are. Okay. But I'm here. All right. So what we're doing here then, we've also sort of loosely talked about the fact that type constructors are functions. They are functions that construct a type. Just like data constructors are functions that construct a value. So right here, since either has 2 parameters and we need it to be like lists and like maybes and only have 1 parameter, in order to write an fmap for it, we have to partially apply the either type constructor to its first type argument. We don't have to care what the first type is in order to do that, because our fmap implementation isn't going to be able to touch it at all, right? This now, right, when we had up here, we have these f's, right, that have to be functors. Right? They have to be some type, oops. They have to be some types that have an implementation of fmap written for them. Then this here, either A, is going to be this f all together. So that A is no longer touchable or transformable or anything. It sort of disappears into the f, and we can't do anything with it. Does that make sense? Okay, so let's see if it will after we write the instance. So what is the instance for this going to look like? We know we have now 1 value left from either, and it is its second parameter, right? The b in right b. And so that's going to be the value that our fmap actually can transform. So we saw with our maybe map, wherever I wrote that, right here. All right, we saw what that looks like here. Right, we saw what that looks like for maybe here. Let's see now if we can write this, but for either, having now, sort of gotten rid of this. Okay. It shouldn't really be parenthesized in the data type declarations, sort of doing that to make them visually similar. Okay, so all right, I have it set up where we have this instance here, and we know from talking about them yesterday, right, that that's a keyword. So, right, when we look at example, right, we can see the list here. We have an instance of monad for maybe, right? We have an instance of functor for maybe. So really we could turn this into instance functor maybe where, right? And then this now would be fmap, like that. Now you also can't really have type signatures in your instance declarations, at least not normally. You can, there's a type extension that allows you to do that called instance sigs, but since we have it, since we can just comment it out, we can just put it there. All right, so what will this look like? Do you feel capable? Do you feel confident? Are you going to write it? We're going to write an fmap for either. We can.
Some pattern matching would be good.
Some pattern matching would be good. Pattern matching is always good. All right, so we can. Let me see if I can remember how to do this. Oh, if you want to be able to do this in your REPL, I forget to tell people. Remember, I was telling you about my GHCI config yesterday. The set X type applications. I have that turned on by default in my GHCI config, but if you guys want to be able to use it so that you can do the same thing I'm doing, then that's how you would turn it on. And we can now get the type of fmap. Is this the right syntax? Nope. Not going to be able to remember, huh? Nope. Because I don't think they'll do it like that either. Nope. Yep. Always forget. So, do you know? Do you? Well, I can just write it. We'll be less fancy. All right, it's going to look like this. The fmap is going to have the type A to B. I don't know why I always forget that. And it's going to give us an either A all that. It's going to have a type, something like that. So we're going to first want to start with some pattern matching, yes. So we'll start with a function again. Instead of nothing this time, what's the case that we want to take care of first? Left, right. I have to remember if that needs to be in parentheses or not.
So why you don't apply the function for the x?
Right here?
Yeah, left and the function is in left.
No, because that x is there.
Just big.
Yeah, we can't. It's just like the nothing and maybe.
Okay.
Yeah, because it's the leftmost type parameter, this thing here, right? That a, which is part of the f. And so it's there. And this a is part of the f right here. So just like
Maybe you could change the signature of H map to B to C so that it's easier to see. But
here,
it's B to C if we compare with the.
okay, that's fair. Like this. So then this would be the B.
The X would be A.
Okay.
Yeah, the X is the A. But the X I have X'd out because we don't want to touch it, right?
And you can't.
Yeah, you can't. You can with bifunctor though. People often ask me that. Sorry, that's why I keep bringing it up, because people often ask me, but what do I do then if I have an either where I do want to potentially transform either side? And we do have a type class for that. It's just not this one. Yes.
Can you explain again why you're not planning function to that?
Oh, because you can't. It's been absorbed into the F. So let's see. Functor, this type class, can only handle type constructors that take one parameter. It cannot handle type constructors that take 0 parameters. Well, those, like bool. And it can't handle type constructors that have more than one. It can only handle ones that have one parameter, that take one argument. So you can kind of see this here, this little nice error message that it spit out at me here. It expects kind star to star, but either has kind star to star to star. How many of you are familiar with these stars? A little bit? Okay. So the star is the type of types. Yes. We can get the kind signature of types. Yesterday you were asking me why we couldn't get the type of type constructors, because what you actually need is the kind of a type constructor. So maybe is star to star. It is a function that takes one type argument of kind star and returns a type. So it takes a type and returns a type. It might be better if they wrote these type, but that's not how they do it in GHCI right now. So that's what that means, that star to star. Either has 2 of them, right? It takes 2 arguments before it returns a type. It's star to star to star. It needs 2 arguments before it returns a type. So how do we get it to be an argument? How do we get it to look like this? Function application. Oops, we can't do it to a variable, sorry. So for example, if we applied it to string, now either string, so let's say this was our A in either A, B, right? Now that has the right kind. Now it's a function of just one input and one result. So now given one more type, it will construct a type. And functor, this type class, can only work with type constructors that are star to star. So they just are needing one parameter and returning one type. Yes?
I think there's an even more intuitive way of seeing why it's impossible to map X, because you have no function from from X to something else.
Right.
Because the either may contain two different types.
Yes.
You can't reuse that function you have there. That's from B to C, that's from X to Y.
Right. That is exactly correct. Did everybody hear and understand? Yeah. Yeah. Because these two things could be different types, right? And so you would need two different functions to be able to map both over this and over this. That makes sense? And that's exactly what you get then in the type class bifunctor. You get an fmap-like thing that has, you can pass it two functions that could be potentially be different types. So then you could have an X to Z function and a B to C and map it over your either X, B and get, well, you would either get, it would either be the X or the B, right? Never both. But if you had, for example, a tuple where they are both present, right? So with bifunctor, you get function, it's called cleverly bimap. So you get a function 1 and a function 2, and then you get some type that has two type arguments, right? So let's say this is X to Z, and this is B to C. And if we're applying it to an either X, B, then the X to Z function could apply to the X and transform it into a Z, right? So we would get either Z, C, because this B, C function would apply to this B. So whichever one of them was actually present at the term level, the function would apply to that and transform it, and we'd have either a Z or a C. With tuples, since they're both present at the same time, you guys are familiar with tuples, right? I don't like talking about tuples. I don't know why. I don't like saying that word tuple. Tuple? I don't know. I've never been very comfortable with the word, and so I tend not to talk about them very much. But with a tuple then, all right, so we have bimap still. We have these two functions, right? If we're going to bimap that over, oops. We're going to bimap our function 1 and our function 2 over some tuple that has an X and a B in it, then both of these functions will apply. This one will apply to the first element, and this one will apply to the second. But we just can't do that with this particular, with fmap. With fmap, it can only ever be the second one. There's just no function to apply to the first argument. All right, everybody's on board?
Call it a pair.
Hmm?
Call it a pair.
A pair, yeah, that's a lot better. So, I often use the pair type, or I write a pair type to represent either when they are the same type, because tuples can vary, right? They're an A and a B, so they can be heterogeneous. But with a pair, I often use that either when they're both going to be the same type, or if I need them to be, yeah, well, really, that's usually when I use that. But yeah, pair would be better. Then I'll have to say tuple. Tuple. Okay. All right. So do we all have our instance written? Did we not finish? You have a compilation error. Okay. Well, what have we done wrong here? We'll call that B. And what do we want to do here? I don't actually have this. Well, what's your compilation error? Is it just telling you that you have a name clash with the either that's already in Prelude?
And there's a currents right. It could refer to something important.
Yeah, it's just, I think it's just a naming problem. We needed to call this something different. We'll call it twice. This act twice. Call this one this. Or you could shut off your prelude. That'll work as well. Oops. Oh, get them all.
The first time I did it.
Arthur. Ah, it's commented.
Yeah, it's commented out, so we should be okay on that one. I haven't actually even saved this, so it's not even registering that it's Haskell yet, but we'll call this instance. I already have one called instances. All right, I'm gonna have to comment these things all out, or else we're gonna have troubles. Let's see. Okay. Success.
Okay. Congratulations.
Okay, so what is yours still telling you?
I just copy your.
Well-
No line.
Do we have some missing parentheses? Do we not have the function being applied in the right place? Do we have names?
Is it possible because I use either and either's I can't overwrite the
Yeah.
implementation of
Yeah, you'd have to turn off the prelude so that then you have no,
Okay,
yeah.
Maybe.
Yeah.
Maybe that's the problem.
Yeah. So did you try renaming it?
Now I'm trying.
Okay.
Yeah.
If you try renaming it, but don't change anything else, try renaming it and see if you had it right, except for the names.
Okay.
Because, yeah, it won't. You can turn off the prelude there's a language extension called no implicit prelude. You can turn that off. So just a minute ago, I showed you we talked about using set in GHCI yesterday for turning on the type signatures, right? How mine always tells me the type of everything I've evaluated.
Mhm.
You can also use set to turn on language extensions. And so, for example, if you are feeling bold, if you really want to learn Haskell, this is what you do. You set no implicit prelude, and then you have to write everything by yourself from scratch, because then you have nothing imported. And the one that we were using badly, but X type applications, that lets you see the type of, say, something specialized. So like if you want to see what the type of FMAP specialized to maybe is, you can use type applications to do that. So.
That's all right.
Okay, now it's all right?
Yeah.
See, you had it right. It's just the names.
Mhm.
Yeah. All right, any questions about this? Okay. Do we feel next like we need to write the instance for tuples? Pairs? Do we need to write that instance? Because they're a little bit different from either. There's still two type parameters. All right, so all right, so that's what the data declaration for them looks like. Like lists, they have this built-in syntax, and so instead of having a name, right, in words, they have the name of them is parentheses with a comma. So they still take two parameters, just like either. We can have a functor instance for them. Will the functor be able to, will fmap then be able to transform the A of a tuple? So you've got, you construct a tuple by doing something like, for, and then we put a string there. And now we have a pair, right? Now we have a tuple. They can be different types. Can I write an fmap implementation that does something to both of those? That does something to the for and to the Julie? No, it's just like either, where with either we couldn't touch the left. With the tuple, we can't touch the left again. It doesn't have a data constructor named left, but we still can't touch it. Our fmap will still have to skip over it. Why? Well, like either, it takes two parameters and returns one result, right? A type. If we, yeah, I didn't think it was going to give us a type for that. What if we have a hole? Yes. But now it says it's already a star. Huh? Yeah. Now we have a type. Right? We still don't know what is here, but now we have a concrete type because we've applied it twice. So it's just like either in that sense. So do you feel like you could write the instance for that? We'll call it pair. We'll need to define a type first. Okay. So unlike either, whereas either is this or that, right? Now our A and our B are both always present at the term level, just like with the tuple, right? We have to have both of them before we have a pair. But how is that going to change what our F map looks like?
There won't be a parametric one.
It won't be a parametric function?
No, we don't have two choices, so there won't. Well, actually, there is a parametric, but we don't have to distinguish between two cases.
Right. We don't have to distinguish between two cases. Yep.
But there will be a pattern match.
Yes. There will be a pattern match, but we don't have to distinguish between two cases. That is correct. Functor. What are we doing? Pair. There we go. All right. All right, so we've just got this B left over here, right? So we're going to have, we can call it again a B to C function. All right. We're going to have, fmap is going to take a B to C function and a pair X, B.
Missing an arrow, right?
Yeah, I am missing an arrow. Okay. And
There is the C.
mm-hmm. All right, so what would this look like? Fmap function over, we've got pair, what should we call them, X and B? Or
Perfect.
did you try it? Talk to your compiler. Talk to your compiler. Show it some love. Huh? You got it? Nice. I just sit here and wait for hoping that you will talk to your compiler. Okay. All right. So it turns out this idea of mapping something, right? Like we've mapped over lists, which most people are very comfortable doing. You understand how we map and apply a function to every single element in the list. And it turns out we can just end up doing that for a lot of types. There is some way to take a function and apply it regardless of what this type wrapper is on the outside, right? We've just given it a method for applying a function to this value to return this. So a functor is a type constructor that has some implementation of fmap for it. So sometimes you will hear people talk about this function as being a functor function, because a functor is a way to lift a function into a context and apply it. But you'll also hear people talk about the maybe functor. No, okay, nobody talks about the maybe functor. Everybody talks about the maybe monad, right? But a monad is just a kind of functor, so it's really the same thing. All right. Questions about where we've gotten to so far? I promise we're going to go back to monads really soon. Yes?
Fixed notation of tuples. Are that possible? Well, I tried and I could not.
Can you do, I'm sorry, what?
In fixed notation. So I can do +2 in parentheses, and that's a bad example. I divide something by 2. Just give out the first argument on the left side, and I have the partial application. So I assign the second argument and not the first. Did I?
Yeah, yes.
So can I do the same with tuple?
You need a language extension for that, I believe. Right? To partially apply tuples.
And could I even do this with either?
Yes.
So I could actually, if I wanted to, address the first argument if really want to. With easier. Come to the F not be specified earlier.
Oh.
Would you say so or not? I'm not sure.
I don't think so. I don't think so. I haven't actually tried, but I don't think so. So I think that so like, you know how I said that often either is used as like where the left is sort of analogous to false or nothing and it's sort of the error. This is why, because you can't do anything to the value that's in it. So if you're returning some kind of error, then you don't want to, you know, transform it in some way. So sometimes when people want to do the opposite, they want, it's actually their error value that they want to do something to, then they just make that their right. But you can also just use bifunctor, and then you could do something with both of them. Bimap.
Running here is either the left has a non-value cannot work with.
Right, you're just going to return something kind of like with nothing, right? With nothing, it was sort of obvious how we couldn't apply a function to that because there's no value to apply a function to, right? So that's how either ends up getting used quite often. You know, since we do have bimap, or since you could put your errors on the right instead of on the left if you want to, then, you know, you can use it in different ways, but that's how it often gets used.
So the distinction between either and maybe is that maybe either has a known or a just, and either could carry if I want to some error value.
Yeah.
But maybe not.
Well, it's always got to have something. There has to be some A inside the left, but it could be, you know, equivalent to nothing, right? Like it could be a left empty list or something like that.
There will be no difference to maybe.
Yeah. Yeah. Okay. So we're going to go back to I think we're going to take a break real quick, and then, because it's already almost 5. So I think we're going to take a break real quick, and then we're going to go back to this and talk about how this, right, we talked a little bit, we started our exploration into functor by talking about getLine and how we get this string out of the getLine, right, out of this IO string, so that down here, it's the string input to this function. So this is actually going to, we needed to talk about functor first, but this is where we're going to start talking about monad. So we're going to go back to that and de-sugar our do syntax into some monadic binds. and it's going to be fun, and you're going to love it. I can tell. Okay, so let's take a few minutes break. Yes.
Yeah, the sticker.
Oh yeah, I do. I have Joy of Haskell stickers. Well, I have our applicative heart operator here. So, and I think I also have some of the. I do have stickers. I have so many stickers. So I have the Haskell logo in purple. I have our applicative hearts. And then I have ones that say the joy of Haskell. Okay, please help yourself.
Thank you very much. When is the book coming?
Joy of Haskell? Well, it was supposed to be sometime this year, but we've gotten a little bit behind because we've gotten a little bit behind. So I think it'll probably be sometime early next year. Hi. I know you from Twitter.
Yes.
How are you?
I know you. Hi. I'm good.
Good. How's it going?
I've made good progress on this event, learning Haskell.
Good. Did you go to the GHC DevOps stuff?
Yes. Also, but today I really wanted to see how you introduce because I'm also looking into teaching others to navigate our meetups. So,
Nice. Well, I'm doing it a little bit different now than I have done sometimes. Mute this. Is that working? Is that working? Okay. All right. So now I'll start coughing again. Sure. Okay, so this is where we left off with our program, right? And we want to understand what the monad is in the do block. So we have a function that needs a string input, and we're not going to worry at all about the fact that strings can be a monad as well, because we don't care at all right now about the list monad, because we're not doing anything with that really. So we have a function that needs a string input, but we want to apply it to a string that is inside another type. That type was IO, right? Because the get line gives us an IO string. And we used this backwards arrow, which is special to do syntax. The only time we can use this backwards arrow is in a do block. So this word do here, right, introduces some special syntax. Because it is often easier and sort of tidier to write things in do blocks than it is with the monadic operator. But that's all it is just some syntactic sugar over that. So we're going to try to de-sugar it here. So we've got this IO string, but here we want to pass it as an input to a function that needs a string. And we've already seen a way with our fmap functions, right, that we can apply a function to a string or some other value, right, that's inside another type. We've done it with lists, right? We've taken an A to B function and applied them to the A inside of just, right? So we get just B. We've taken them, we've written it for ethers. So we know we can get over that either barrier, right, and apply our function to the value that's inside of that. And we know, we have seen that we can also do that with IO. So we know we've got this function called fmap. We know we've got a functor here. We know we have a type that has an implementation of fmap. So we know we've got a functor. All right. So we're getting closer to... Sorry. All right. Then we've got check input. Wait. Why am I the one that returns a bool? We don't want that. We don't want a bool. We're done with bools. All right. So check input here. It still takes a string as an input, and it's going to return a maybe string. But we've got, oh God. All right. We've got terminal. Yes, terminal. Okay. We've got this print function here, right? Let's look at the type of print. Oh, this type class constraint. Means that it takes as an argument any type that has an instance of the type class show, which just means it's something printable to the screen, which obviously strings are, right? All right, so print will take some value and returns this IO unit thing that we've talked about, right? Which means that it does some effect, meaning prints it to the screen and doesn't return any other value. Okay. So that's all the things that's going on here. Let's take a look at, well, first let's annotate some of these, right? So we've got here, this thing here is a string, but this thing that's on the other side of it is an IO string. We know that this thing is a string because it's down here, it's an input, right? So, but it does have the IO sort of in front of it. Okay. So then we could, let's get rid of this do, and let's get rid of this backwards arrow. Right. So now we're going to take our get line. It's going to be our first thing. And that gives us an IO string. And we want now to pass this IO string as an input to the check input function. So we want to pass that IO string to something that takes a string and returns, does check input return? A maybe string. And then we want to pass that, right? After this, we want to pass that to something that takes something, right? Something, some type, and returns an IO unit. Right? That's what we need to do in this do block. That's what we were doing in this do block, right? And now we're just sort of desugaring it so that we can do all that without do. All right. So let's deal with this part first. So we have a function that actually I think I'm going off of the plan now. I think I got off of the plan. Yeah. Yeah. All right. That's all right. We're gonna roll with it. Okay. So we have a function that can do this. Okay. That can pass this IO string, this wrapped string, to this function here. It's a little bit like fmap, but there's something else going on here, right? Because this fmap takes an A to a B, but we have an A to like an FB, right? We've added some layer of type inside of that function. So we need something different from fmap. Similar, right? But also different. Okay. This is going to be a little bit weird because we actually have two monads that we're working with here, IO and maybe. We're not touching the string one at all. But we have two that we're working with. So this is what it's going to look like when we desugar it. So what we had here, written like this, our backwards arrow, written with monadic bind, looks like this. So we need to talk about this, unless it's just obvious to everyone how we got there. Let's talk first about the type of, I'm going a little bit out of order. That's all right, because I need to hurry. Okay, let's talk a little bit about this type operator. This is the main operator. Just like fmap comes from the functor type class, this one comes from the monad type class. It's the main operator of the monad type class. And you can see that we have a wrapped type where, as the first argument, right, a wrapped value. So we have an M that's the monad. So it could be maybe, could be IO, could be a list, could be either, could be a pair. That we take this A from it and we pass it as the first argument to a function. That function inside is making another sort of layer of that type. Right? So just like we had here, right? This string gives us back a maybe string. Right? Inside that function, instead of just being A to B, it's A to some other type B. Right? So we get some extra typiness in there. Okay? Now, you may notice that in what we have, this maybe and this IO, these are not the same M. But in our type signature here, they have to be. We're getting there. I promise. You guys are looking very skeptical. You are skeptical? No? Okay. So what do we have here then is, I forgot I can type instead of get up and write. So we have here our MA value, right? Get line is our MA. So the M for this is IO and A is string. All right, no problem. Now we're going to have to, oh, that's not what I wanted at all. Text editor. All right, so what we're going to have to do is do this weird thing, right? We have to once again pass this anonymous function, right? Pass the argument, because it has to come all the way over here. So we're going to take it out of the get line. We're going to take this string and put it here. This, we're not going to worry about print for just a minute. This is going to be our string to maybe string function, right? This is going to be our A to MB function. Remember our type signature here. It's complicated a little bit because we have a couple of monads at the same time. This is easier if you start with just one at a time. We are going for it. We're going to do it. Get rid of that. It's because we will remember that the M's have to be a monad, right? In this case, maybe and IO. So here we have this A to MB, but this isn't the same M as this. So we have a problem, right? If we got rid of the print, anyway, we would have a problem. Right? If we had this, this could work if this was returning, if check input was returning an IOB. But check input is returning a maybe B. Right? Check input's not doing any IO at all. So we pass this string to here so that we have our string to maybe string function. All right, so then to get this MA, that's why we had to add the print. This is a bad explanation. I'm doing a bad job today. All right, so we add the print because then there's where our IO is going to come in. So now the print is our A to MB function. But inside of it, we have this. You notice that we don't need any monadic bind for that, right? In here, we have just a maybe string value. And so now our A to MB function is going to be a string to IO. What's the result of check input X? What's the type of it? Maybe string. So we're actually also, I said we're not using the list monad at all. We're actually not really using the maybe one here either, right? This is all, we're only dealing with the IO monad here. So we take this IO string, we pass it as a string to a function that generates an IO maybe string. And now you see this bit of ugliness here. I mean, that's why people use do syntax. Right? It's one of the reasons.
This works just print an implementation for the argument of type maybe string. Otherwise, we would have to apply another.
Yeah. So as long as print, right? This A, even though it just says A, but it's acceptable for it to be actually two types sort of stacked up into one, as long as we consider them to be one type. So in this case, this works because it can be any type that has an implementation of show, and both maybe and string do. And so maybe string is our A or our B. Yeah, our B, right? That's the B. And the IO, of course, is the M. There we go. Look how nice that is. So our IO is the M, for our bind. String is the A, maybe string is the B. That's why when we use this in the REPL, what? Oh. There we go. All right. That's why when we use this in the REPL, notice how it's still returning a maybe. Right? Because it's an IO maybe string. Questions?
Takes any type which is a monad type, but for either it could be different type. So it actually unwraps the type which is different, which not check value does not expect that. So the X here is the type string, but for either it could be int or string. What is going to happen in this case?
What is going to happen in that case when you have either?
Yes.
So
this is binding unconditional, right? So it's always just take something from monad and then apply it to the next function. But if we remove string, check input x, expect string, not int. And it could be int.
well, remember I said that monad is a functor? So when we write a functor instance, so let's look at the maybe functor instance. I've called it possibly here to avoid name clashes, right? When we wrote the maybe one, right, we have to always just return no if there's a nothing, right? But remember when we wrote the either one, then what did we do with the first value? What did we do with it? We did it somewhere, right? I don't know where I put it now. Somewhere. Oh, here, yes, here. So when we wrote the functor instance for either, we partially applied it. And so the value on the left disappears just like nothing, right? So in the same way that monad can't do anything with it, in the same way that functor can't do anything with it, neither can monad. Monad will always just stop the first time it hits a failure. The first time it hits a left. It can't evaluate any further because there's no value for it to apply a function to, just like with fmap. Does that make sense? We could write the monad instance for, we'd have to write the applicative first because you can't have a monad without applicative, but we want to do either, right? Okay, so we won't worry about the applicative. We're not probably going to have enough time to talk about them today, but have to have an instance of applicative. So, oh, the applicative is, we have this. All right, we want, sorry, I'm very tired, and I don't know if I can do this. Wait, we'd first have to have a monoid constraint on the A. So let's just go back to the ones that I've already written. Okay. Yes. Here we go. This is what the monad instance will look like. So we have a data type that's just like either here, rename so it'll compile. So there's the first, right? There's the left, and there's the right. It's the B. So remember with the functor, whatever function we were trying to f map over first A, it can't transform that, right? It can't apply to the A. It can't apply to the left. It's the same thing with monad, because monad is a kind of functor. And so when we have this monadic bind, if there's a first A, we just return the first A. So we would just return the left A.
This is an agreement, right? We don't know if it's easy type, but it's not a merge. To which one should apply? Don't follow the second one.
It always has to be the second one. That's what I'm saying.
It's always the second one.
Yeah, it can't apply to the first one. As far as bind is concerned, just like fmap, as far as bind is concerned, there is no value there. It's like, to us, it looks like we have a left string of some kind or a left int or something, but bind can't see that value inside the left.
And it always works for two types. So if there are three types, it's not going to work.
Right, you'd have to partially apply it twice to get it down so that it's just a function of one parameter, right? Yeah. Does that make sense, what we were just talking about? More or less? So because monad is just a fancier functor, it's the same sort of rule applies, where this, we could call this either so that it would be less confusing. Right, these names. Just that it won't compile because of the name clash, unless I turn off my prelude, right? All right, so when we write the instance, when we look at the implementation of bind, because that's all an instance is, right? It's just like the type class declaration has the type signature for us. And just like I gave you a type signature for map or for fmap, and then you just wrote the function. That's what the instance is. But the compiler, looks up which instance you're relying on by the name, right? And so we have these instance declarations, and this tells us how our function is implemented. So for either, you can see that just like with maybe, it just can't do anything with this left value, the left-hand side. And just like the fmap that we wrote for either, it just can't touch it. It's like it doesn't exist. So when you have monads, if you're chaining a bunch of operations together using bind or sequentially with do syntax, it will just always stop the first time you hit a left. If it's the maybe monad, it will always stop the first time it stop evaluating, and just return the first nothing that it hits. So that's a good question, but it actually stops. Whereas applicative evaluates both and then propagates the nothings. Does that make sense? Yeah. But monad, because monad is designed to sort of operate sequentially, and because you can rewrite like anything that you're chaining together with monadic binds like this, usually you could write them as nested case expressions. So just like if we had gone on and expanded on our palindrome and maybe nested some more case expressions here, right? So we come up with some other rule that we want to apply, and so we nest another case expression in here. When you look at it as nested case expressions, you can kind of see how it must just stop there, right? As soon as it hits a nothing, it's just going to have to return that nothing. Right, as it goes down the cases. Now, that's not literally, because of laziness, that's not literally necessarily what it's doing, but that's how it's going to have to conceptually happen. And so, yeah, it'll always return the first one. And so, for example, if you go and look at, sorry. Oh, I was already on my GitHub. So if you go and look at, this is public, and so you can go and look at it. It's from a presentation I gave about the difference between applicative and monad. if you go and look in here, for example, and you play with this anagram example, you can see here we had some nested case expressions that we were then able to collapse with a bind. And you can tell by giving it different error messages, right? Here, this left says empty string, and this left says not a word. And so you can tell very clearly which one it stopped at. And Monad will always have to stop at just the first one that it hits. The first left or nothing or empty list or whatever. It just has to stop. Applicative, on the other hand, can evaluate both arguments. The applicative, the little TIE fighter that our heart is modeled on. It can evaluate both, but then it propagates the error. And you can tell that that is true because there is another data type, and that's what this presentation here was all about that I gave. And so you can look through the code, and the talk is actually online if you want to watch it. But because this is old now, and so it's no longer called ACK validation. It's called just validation. And it's the same in type as either, except for its applicative instance is different. And it will allow you to accumulate errors in the left instead of stopping at the first left. Yes. And it's really cool. So I have, like I said, I have given that talk, and I also, and I think it's, so this is actually this is another approach at Monad. And this goes at it from the side of, we have a bunch of nested case expressions. So how do we reduce those with a bind? So that's what this post is about. And then I also have this one here, applicative and Monad. This is the talk that I gave about validation. Validation is a really, really cool type. I think. So, and we didn't, what time are we at? Oh, we have time still left to talk about monoids, because we haven't talked about monoids at all. And on Twitter, I'm known as Monoid Mary, so it seems like we should. But the way that the validation instance works, the applicative, is that it uses a semi-group, which are like monoids, to accumulate the errors, to concatenate the errors on one side. And so then it can return all of them to you, even though it propagates the errors. But it's really cool. Go back to which?
The version before. There are some first and second level implementation of counter.
This? First and second. Where was that? I think we're... We have too many things open, and I don't know where we are anymore. This one. Yes. Yeah, there's the applicative there, and you can see that it always will propagate the error, but it does evaluate both, whereas Monad just stops. So what's going on here is that the first argument to that operator, this is the operator. You can see, right? Doesn't it look like a TIE fighter? I think so. But the type of this, right, is this wrapped function. So if we look at that, right, this is the type. So here, this is our F. right? This f is a function that's from a to b. Then we have here our fa. Then we apply to that. And give us a b because this function here goes from a to b. So applicatives are another kind of functor. We have a lot of kinds of functors. We have, or well, really, well, I guess, yeah, we have a lot of kinds of functors. So some types, there are a lot. Functor is like the biggest, and then applicative is a little bit smaller group of functors. Monads are a little bit smaller. Bifunctor is probably a little bit smaller. I haven't actually counted them. I'm not sure they're countable because you can always make new types, right? And then make instances for them. But so bifunctor needs, something like either or a pair where there are at least two type parameters. Then we have contravariant functors, which are really interesting, and I've recently given a talk about those as well. And we have then profunctors, which are a combination of contravariance and bifunctor. And so there's all these functors, and for each one of them, they give you some way to take a function and apply it in some kind of context where it wasn't originally. So just like map lets you apply a function to every element in a list, all of these other functors are giving you ways to put that function into some other context. All of them. In some very core senses, they're all the same. And you can implement this thing right here with fmap and one other function. So they're all built from fmap. Which is why we spent a lot of time talking about fmap and much less time talking about bind, because it's just another kind of fmap, but because you get some extra, oh dear. Let's see, there we go. Because you get this extra layer of m generated inside the function. I mean, it looks backwards, right? It's backwards from fmap, but it's this, right? In fmap, in normal fmap, the function comes first. There is a flipped fmap. Well, sure, because sometimes you want them to be backwards, just like bind. Right? So bind, they come backwards, but they're really the same thing. And so if you want to instead think of, flip bind, that's how you would write flip bind, right? Obviously. Then flip bind is going to look much more similar. So now if you compare those two type signatures, now you can see the similarity. What's needed to make what the difference is between this and this is that when you generate this extra layer of structure, you need some way at the end to come out with only one layer, right? Because otherwise you would come out with MB. You understand why? And because we've got this type that appears here in our function. It's not going to just disappear, right? So we have to have another function that makes it disappear, right? That smushes the two layers into one layer. We call it join. It's one of the methods of the monad class, and it is the difference between fmap and bind. Is that bind, this thing here, is just a combination of, okay, really if you were going to implement it like this, there has to be more than one dot there for complicated reasons. But you can implement bind yourself with a combination of join and fmap. Fmap you're very familiar with. Join is really kind of not that exciting. Join's not in the prelude. So all it does is take an MA and give you back an MA. That's all that join does.
The M's are all the same.
Huh?
The M's are all the same.
Yes, the M's have to be the same. That's why when we were working with our sort of overly complicated example here, right? That's why we had to have that print here, because it can't, if one M is IO and one M is maybe, it can't smash those together. So they have to either, you know, both be IO or both be maybe, and then it can just smash them together so that you only have one layer. So fmap is pretty easy to understand, right? Bind is the same thing, except for some reason, the arguments just sort of go backwards. And at the end, you have this joining so that you kind of smash two layers of type together. Applicative does it a little bit different. Instead of having a join, applicative relies on there being a monoid. And so then we would get back to talking about my favorite thing. Or a semigroup, I suppose. Right?
Can you show your Twitter feed?
Oh, sure.
I've just sent this example to your Twitter feed.
Oh, you did send me a...
Yeah, that's the, you do the get line and the print line.
Nice.
And you just can do it with fmat print line and get line.
Yes.
Do the join in the front. Then you can make join and fmat print line into one.
Yep.
You do it into a bind, and then you get bind and print line and get line. That gives you the bind operator.
Nice. Thank you. Oh, I have to give you a retweet.
Thank you.
All right. There's that $sign too.
Yeah.
Very important. All right. So any questions about what we have gone over? Yeah, I'm not going to be here tomorrow to talk about monoids. So you're going to miss my monoid spiel. But people specifically said in the survey that we passed around, people specifically said, what is a monad? So now have we answered that question?
Yes.
What is a monad? There's a type class called monad. Monads are the type constructors that implement monad, right? There's like the three things kind of all go together, right? Like I was drawing that picture, I had the little triangle yesterday, right? The type class declaration, so that's monad, right? Monad and the type signature for bind, and the type and the instance, right? Those three things kind of go together to form a single structure, and sort of that's what a monad is, or a functor. But you can also think of it as, you know, these ways, functors are these ways that we have of putting a function, applying a function into some context. So instead of having an A to B, now we have an FA to an FB, right? Or a list of A to a list of B. The list is just an F. So I hope that we've answered the question, what's a monad? I felt like like I needed to answer that question. So we put off talking about monoids, and people watching on the internet are going to be disappointed. Does everybody know already what monoids are? Well, I know you do.
Sorry?
I know you do.
Yes. Learned it from you.
Do you want to know what monoids are? We have like 10 minutes, and I can tell you what monoids are.
Yes.
Yes. Okay. I can't believe we've gotten through 3 more hours today, and you guys are all still here. You're all still engaged. All right. So monoids are really neat. Monoids for me have kind of a very special meaning because for me, as I was writing Haskell book, I've told you before that like I was kind of learning Haskell as I was writing the book. And so I was working on I think it's chapter 6 now, chapter 5, chapter 6 about type classes. I was working on that chapter and thinking like, okay, I think I kind of understand how type classes work, right? Addition is defined here in the num type class. And so all of these numeric types have some kind of addition implementation. Eq is defined here in this type class. So all these types have an equality definition, right? And I was thinking, but I was kind of also thinking like, what really is the point of doing it this way, right? And it wasn't until, so at the same time, my co-author had started working on the monoid chapter. And he sent me the beginnings of that. And he said, okay, there are sort of 3 canonical monoids that we think of. Addition, say for integers, because we're not going to get into the implementation details of different kinds of addition. It turns out that some kinds of addition are not associative. Who knew? Me as a programmer, I mean, programmers all seem to know that. And me as a non-programmer, I had no idea that there are kinds of addition that aren't associative. Okay, so he sent me, I think I need to write bigger. Right? So addition and multiplication and list concatenation. Is this visible enough? Okay, I need maybe a darker, yeah. Can we go back to the purple? I had a darker pen yesterday and then he said, okay, these are does everybody understand what list concatenation is, what this operator does? It takes 2 lists and turns them into one, right? Like adds 2 lists together. So he said, okay, these are the sort of 3 canonical monoids. And I was like, yeah, I don't know what the point of this is, right? These are very different things. Addition and multiplication are very different things, aren't they? And list concatenation is also quite different from the other 2, because for one thing, lists are not a concrete type like integer. They're a type constructor, right? So what is this nonsense, right? I was thinking to myself, well, they also have some things in common, don't they? They all take 2 arguments, right? So they're all binary, right? They each take 2 arguments. They're associative. What does associative mean? Right. It means if we add something else out here, right? It means it doesn't matter if we put the parentheses here, right? Or if we put them here, the answer will be the same, right? All 3 of these are associative. What's one other thing that they all share in common? They all have an identity value, right? Is it bad?
No.
Oh, why are you laughing?
I was referring to another joke.
Okay.
There's.
You have to share it with the class then.
Yeah. There's like, do you watch John Oliver?
No.
And he did this Rudy Giuliani. He said 0, and John Oliver was 0. So that's basically what they have in common, right?
Yes,
0.
The 0. Except for sometimes it's a 1. We have 0 boys and 1 boys, right? Okay. So they all have an identity value. For addition, it is 0. For multiplication, it is 1. And for list concatenation, it's an empty list. So a monoid, now, as I was just saying before, where there's like, it's not, a monad isn't just an implementation of bind or just a type, right? They have to kind of go together. So a monoid in Haskell is a type that has an operation that is binary, associative, and has an identity value. It's a surprising number of types. But the really surprising thing about monoids is that for almost every type that is a monoid, there are two, at least two, sometimes many, many more. Why should that be? I mean, clearly for integers, there's more than one, right? This is the exciting thing to me about monoids. This is when I really started to get excited about Haskell. Okay, because we have, and I gave a whole talk about this in London last year. So I can just recreate that for you right now. Okay. We think about, maybe I should do this in typing though, because that shows up better, doesn't it? Okay, if we think about monoids, if we think about binary associative operations, we'll go to this one. Okay? Addition and multiplication, I said, are very different. Right? There's some similarities that we've pointed out, and those are the similarities of what we're focusing on when we call them a monoid, right? They do share both of those properties, but they're also quite different. In the same way that, for example, Boolean disjunction and Boolean conjunction, you know what those are, right? Oops, I need a terminal. So we have, we wrote all, and for all we use this, right? And we also have this that's an or, right? So this one is an and this one is an or. And does everybody know their Boolean truth tables? Right? Each of those is a binary operator, right? They're associative. They have identity values. Right? True in the case of and, false in the case of or. So we're seeing a pattern, right? Seeing a pattern where and is a bit like multiplication, right? Its identity value is true, which is sort of like a 1, right? Or is a little bit like addition. Its identity value is false, which is kind of like a 0. If you think of it maybe in terms of binary addition and multiplication, it might seem a little to make a little more sense, right? We also have some set operations that are very, very similar, right? Union and intersection. Although the ones that are closer to being like addition and multiplication are actually disjoint union and Cartesian product, right? So over all of these different types, Booleans and sets and integers, right? We have this pattern where there's at least 2 ways of doing a binary associative operation with an identity value. And so this holds true as well in Haskell. There are, for most types, if they have any monoid, they have at least 2. Usually those monoids will be a monoid of, let's call it a monoid of choice, so something that is disjunctive and works more like addition or list concatenation, or works like a Boolean or, where it picks one or the other, but not both. Sort of like a sum type. The other kind of monoid then that they would have are the conjunctive monoids that work like multiplication, or a thing that we have called list zipping, or Boolean and. And so this pattern persists across all of the types that are monoids. Well, maybe not all. All is a big thing. I hate to go universal when I haven't actually proven it, but it's very, very common pattern. So when we write maybe monoids, for example, now in Haskell, every type class instance has to be, unique for a type. So we can't have an instance monoid ABA that does one thing and then another one that does something different. And so we have to give them all different names. So we have these new type wrappers to give these things different names. So we have the first monoid for maybe picks the first just. The last monoid for maybe picks the last just. So if you have two justs, it will return the second one to you. There's also a maybe monoid, and I believe the default maybe monoid in base combines the two of them. So if you've got a just appended to a just plus a just, then it combines the two values and returns just A plus B. So that was the really exciting thing for me about monoids, is just that you find this pattern over all of them. Okay, I don't know about all, because I haven't proven it. Like I said, I don't know how you would prove that, but it's very, very common, at least. So here, for example, we wrote this instance, this monoid instance. So mempty is what we call the identity value of a monoid. Mempty. That's the identity value. And mappend, or you'll often see it written like that, is the concatenation or addition or multiplication, or however you want to think of them. We just call them append because any more specific word has too much, would tell you too much about what implementation you're talking about, right? So that's my spiel about monoids. I'm not sure that it's very useful to you when you're writing code, but that's what I think is really cool about monoids. So this one here, you can see that this one, let's see, the mempty is no. So that's the nothing, right? If we're going to do this about maybe, call it by its real name. Anything that we're appending with nothing, we would return nothing. All right, so down here we have some choices, right? We have decided to go ahead and propagate this error, right? We didn't have to. We could have appended a nothing, like if it was a just A and a nothing. We could have disjunctively, we could have chosen to just return that just A. We don't have to return the nothing, right? Because there's nothing here that we're just combining things, right? And so we don't have to apply a function anywhere. It's not like a functor where we had this function that has to get applied to some value. Here, we're just sort of combining things. So we can combine things by choosing one or the other, like we do with sum types, right? True or false, they're both values of bool, but we just always pick one or the other. Whereas like a product type, we have to have both of them, right? That's conjunctive, like multiplication. Very conceptually like multiplication, because it's like a Cartesian product of sets.
But I thought that given that we had named nothing as being the identity, this would be the only way to do it.
Hmm?
I mean, we've made nothing the identity.
Oh, sure.
So append with nothing would always return the other value. Shouldn't it?
Yes, it would. We don't have, right now, we don't have a consistent, is that what you're saying?
Yeah.
We don't have a consistent instance because I've been sort of just changing things and not keeping them consistent. Yes, you're right. So anyway, that's what I think is really cool about monoids. So that's my monoid spiel. The monoid instances are not very hard to write because you're just always combining. You're just always either picking one thing, one side, or you're combining them somehow conjunctively. But just like we have some Boolean monoids that are named the same as the Boolean functions, one of which we wrote, right? All. And there's also any. All gives you a true only when they're all true. The all monoid does the same thing. So if you have a bunch of Boolean values and you want to combine them with a monoid operator, like this operator, you would have true. This would be the monoid for bool. We'll just call it bool because we're not going to compile it, so it's not going to complain at us about the name clash, right? But you would have true and true if this was all, right? The all one, then that would equal true. Every other case would have to equal false because that's how alls work, right? That's how conjunction works. Oh, I left out the mempty, didn't I? So the mempty for an all is, again, what I'm writing here is not going to compile for various reasons, but conceptually this is the case. What's the identity for an all or for conjunction? Yeah, just like when we wrote the all function, right? Any value that you append with true, right? Any value that you this looks just like a truth table, doesn't it? The truth table for and, right? True and oh dear, true equals true, true and false equals false, false and true equals false, false and false is so that would be the same thing for our conjunctive. This is this specialized bool. That's all. That's all the secret behind monoid. It's not much, is it? And then we could write in any, right? So this one was all. We could write in any. These all exist in a module in base called data.monoid. We write in any, and this would be like disjunction. In which case this, right, this append operator would be equal to this. That's really it. That's all there is to monoids. But okay. Yeah, go ahead. Duplicative? Yep.
So you say that the click normally should contain all those so it's just propagated. But this seems the opposite. It's not long.
What do you mean?
So if we have error already, it returns the error. But it doesn't have error.
It doesn't what? I'm sorry.
It should return two errors. So if applicative applied twice on error state, left side state, it will false error, right? For one.
So what's happening is applicatives sort of rely on implicit, and they are implicit unless usually they rely on implicit monoids. And so when you evaluate something that has, say, a nothing, let me see. If you evaluated something that was like a nothing on one side and also a nothing on the other, the reason it doesn't return two nothings is because maybe the maybe monoid says that when you have a nothing and a nothing, you return nothing.
But then we don't know what the answer was. If we apply to function is alpha is numeric twice, so we're going to receive one nothing. So we don't know which of them failed.
Right. You don't unless you have something like either or validation that can tell you, right? Where it can carry that information with it. So the either applicative is written in a way such that it'll only return one of them. It'll just tell you one of the left errors. But the validation applicative is written in a different way. The instance is written in a different way so that it can concatenate all the errors and return all of them to you. But yeah, it's because there's always, for applicatives, there's always some underlying sort of monoid or semi-group instance that is telling the applicative what it should do when there are two errors. Does that make sense? Okay. I don't think I've ever tried to tell that to somebody and had it make sense that quickly, so I'm a little skeptical, but you can see it when like with tuples, because there's a, well, it's after 6, so, but you can see it better with tuples, like that there's this implicit monoid, because if you use the applicative with tuples, whatever the monoid is on the tuple, on your A of your tuple, right? Because like applicative is a functor. And, yeah. So, oh, well, actually, I wrote a blog post about this too, so you could just read that, and then I can stop talking. So, yeah. I'm pretty sure I did. No, that's not my blog. Let's see if we can find it, though. Monoids. Yeah, there. I actually wrote about this exact question. Yeah. So see how with tuples, see how you've not given it any function telling it to concatenate those strings, but it does because there's a monoid instance on the strings, so it knows what to do with the A's, and that's why you don't end up with 2 layers of tuple too, right? You have 2 tuples there, and you should end up with kind of like 2 awkwardly juxtaposed layers of tuple, but you don't because of the tuple monoid. All right. Any more questions? I have to be honest. When I showed up here at 3, I did not think I was going to make it for 3 hours, but we did it. Wow. Thank you all for sticking with me. I made a lot of mistakes today, and I'm really sorry, but hopefully it wasn't too bad.